Alright, this is a pulsing light seeker that I've been working on. This is the second model, and I just got it working, and I gave it these indicator LEDs so we can see what kind of logic the sensor is seeing. The sensor's a lot nicer than the last one. The sensors like that, and they come through on there. And then this is a breadboard with it has 4 amplifiers using the 2 and 7000 MOSFET in MOS, and it's they're capacitively coupled to each one of these photoresistors, which are in series with a 10K resistor from positive to ground, and in between those two there's a capacitor that hooks to the base of each one of these 4 MOSFETs right here. These MOSFETs have 100K going to the 30 volt rail and 100 ohm going to the negative rail. The boost converter takes the 5 volts and turns it into 30. So there's a 30 volt rail and a 5 volt rail. The grounds are shared. And then the signal is a very small signal is amplified by the capacitors because they're on the Q points, and passed through a 2-stage voltage doubler, which is all these capacitors and diodes on the closer side of the blue ribbon right here. At which point they're then passed through these voltage regulators I made using just a simple BJT transistor that has a diode from its collector to its base. So, and in low voltages, the diode's off, so you read a huge voltage at the collector, but once you go past about 1 volt, the diode becomes active, shorts the base to positive, and you can't have more than about 1 volt, which is good because these voltage multipliers are putting out 30 volts, 25 volts, because the signals can get so powerful sometimes, and your Arduino can't read that, so problem solved. Now, each one of these 4 BJT generic 2 and 3903s, or 304s, then feed to the analog pins of the Arduino board, and they're pulled low by 4 10K resistors, so I can show you that over there. And right now I have it picking up any signals greater than about 5 millivolts. It's pushing the 10-bit analog to digital converter as far as it can go, really. And then, this is the kicker, different from the last one. You see them right here. Each one of these LEDs represents a sensor or a direction in turn. So we have the left right here is green, red is up, right is yellow, and down is blue. So if I shine a light off on the left quadrant, that is the green LED, and the green LED should turn on. There it is. And this is pretty actually incredible because I'm doing this in almost direct daylight right now, and even in the direct daylight it's still able to pick up that spot 10 feet away. And you can see this is pulsed right now. This is the way this flashlight dims itself. This is half brightness, is by alternating at about 1000 hertz, so it kind of halves the duty cycle. But if we go to full brightness, the LED doesn't pick it up because it's not wavering. But half brightness, come on, there you go. See? And now we can move the spot around, and as I move it into the other quadrants, for instance down, the blue LED will turn on. And the reason you see it flashing is my shadow is moving over it. That can be solved by a better high-pass filter. So I move it down here, and now the blue and the green are on, because it's in the bottom left quadrant. And I move it over here, and now the yellow's on, because see, yellow is right, so it's in the yellow quadrant. So this is a fantastic little logic device right here. That is, it's working in the daylight, which is incredible. Another problem I found is the resistor scaling issue, because these photoresistors are great, they're very sensitive, very big, but the balance resistor you need to connect them to ground, because the way this operates is these photoresistors are in series with another resistor, and where they connect you take your capacitor out and that's your signal. Now that's great. And you usually want to make your other resistor in relation to this, in relation to your sensor, about the same-ish. Maybe take the square root. But these resistors, these photoresistors, depending on the ambient light level, can have resistances from like 10 or 20 million in the dark, the pitch black, to 100 or 200 in the very bright daylight. So if you choose say a 1K resistor to pick up small deviations in the photoresistor when it's in very bright daylight, around 500 ohms, that will work fine. But if it becomes nighttime or pitch black, now you have a 1 kilo ohm resistor in series with a 5 mega ohm resistor, and the small deviations in voltages might not get detected, and vice versa is true. So that was a sensitivity scaling issue that I might have thought of a solution for, but this seems to be working now, so let's run with it.